We'll be re-deriving the Debye shielding considering both the ion and electron temperature. So the question here asks, to re-derive the Debye shielding, allowing that electrons and ions may not have the same temperature, which is different from the regular definition of the Debye shielding, which only considers the electron temperature. But we want to see the electrons have temperature TE and ions have temperature TI. So it's going to ask which species will provide the dominant shielding if the temperature of the electron is much greater than the temperature of the ion. And finally, calculate the resulting electron density and verify that the test charge is shielded by showing that the total excess charge is negative Q. So to figure out the bishielding, we'll have to use a lot, of course, the electromagnetic equations, the famous Maxwell's equations here. You're going to want to know the potential, because shielding is when the charge becomes zero, and then the potential is going to show a lot about the charge relation. And we're going to want to know the energy. We'll see later why. Actually, this later is right now. So for the Boltzmann distribution, and we want to know the charges that we're dealing with. So one charge we're dealing with is going to be the plasma charge. This is going to be the distribution of charges. And then another charge we're going to deal with is the test charge. So whenever you do shielding, you want to have a test charge that you're shielding. So we'll represent this as 1Q and a delta function, which says that it is a single point in space. All right, so now that we have everything here, let's go through the whole process. So first thing we want to do is to figure out a lot of different assumptions about the state of the plasma so that we can have a working model to play around with. One of the things we know is that, reason why I brought up the Boltzmann distribution here is that we're going to have a plasma. And the plasma we're going to assume is in a steady state, like kind of equilibrium. Also known as, for now, it's not the actual definition, but it's basically the same, which is saying that the energy is kept the same, so adiabatic. And knowing this, we know that means there's a even energy distribution across everything. So as you can see, there's the particle distribution function here, but then the function it's to the power of is e to the power of negative energy over kBt, meaning that this is a function of a Gaussian distribution of energy, because temperature is a form of energy, and then on top of course, is an explicit form of energy. So then now you have this. What other kind of energy are we going to have to be dealing with? Well, of course, it's going to be the electric energy. So we replace this energy with Q phi, which is going to be the electromagnetic energy of the particle distribution. And then you can simplify this, since constants are overrated, just take out the kb, and then you're going to be left with the species of any particle is going to be the maximum species times the distribution, which is negative charge times the field over the temperature. So let's create one for both ion and for electron. Over here, you'll have the ion term, and then over here, you'll have the electron term. Just a quick note, the reason why you say ZE over here is because when you look at ions, what we're assuming is that ions are basically a clump of protons. It's basically the nucleus of the atom, while electrons are by themselves outside. So each electron is going to be just one charge, which is E, but then each ion is going to be a group of charges, depending on which element this is. Okay, so another assumption that we could make. So the first assumption we're assuming is that it's steady state and there's no energy being put in. So it's a Boltzmann distribution, which looks like this. Energy and then n. The second assumption we're making is quasi-neutrality, meaning that the number of protons equals the number of electrons. Why is this? Well, in most materials, most things are neutral. When things are charged, they tend to attract other things until they become neutral. So basically, in a sense, this is almost always going to equal this, or off by a very small deviation. So we can assume that this is the same. And then over here, this we won't have to go into right now. This is going to be used for later. But it's interesting to see that we can combine this term with this term over here just simply by substituting E, and then you can get this relation. And okay, cool. So now we can try figuring out a little bit more of the relation. So actually from here, when we are trying to look for shielding, what we notice is that, okay, we want to try looking for the potential, the electric potential. And in order to find the electric potential, we could plug this in and then we see that it directly relates to the charge. So you could go either way. You could find the charge from the electric potential or the potential from the charge. That's why it's good to know this relation. So from this, then we know that we want to first find the charge to find the electric potential. And over here, we could just simply plug in what we already know from the top. So the potential is going to, or the charge is going to be the charge of each species times the density of each species. And then you plug in the Boltzmann distribution for both of them here. And then over here, later we'll make a few more assumptions. So let's go to the advanced side notes for now. You can skip this part if you don't really want to know how this works or why we make these assumptions, but I'll write this just in case you're interested. So let's go over, let me subtract, actually, let me keep this here. So the first side note that we want to see is that the Boltzmann is good when the frequency is lower than the plasma frequency. So it's also going to be lower than the thermal frequency, which is basically thermal velocity in a given length. So that's one of the assumptions that we can make to say that, okay, this is in a steady state and we can apply the Boltzmann to it. You can derive this by yourself. This should be pretty straightforward, or it could just be an assumed state. And then the second one we want to do to figure out this assumption, which is the Taylor expansion, which we could end up getting like this really nice answer with, is by showing that, okay, this Taylor expansion is actually possible because the difference for E is actually very small. So basically saying that the exponential term is small. So why can we show this? Well, over here we have e to the power of the energy, electric energy over the thermal energy. So we basically want to show that the thermal energy is significantly greater than the electric energy, so that e is to the power of a small number. To show this, let's just get the electric energy here, and then from just general knowledge about the energy of a particle, it's going to be 1 over 4 pi epsilon times e squared over r. In this case, we want to set r equal to the density to the power of negative 1/3, because this is, we're working kind of in spherical. This is just a rough estimate, but it's generally the case. And next, we just divide this by the temperature. just to get the ratio. And then we can get this value over here, which is basically going to be the Debye length, the quote unquote species independent Debye length, which is the normal definition of Debye length, times the density to the power of negative 2/3. And then you can simplify this by putting these together into density times Debye length to the power of third to the power of negative 2/3. So over here, you will know that this n0 times Debye length to the power of 3 is actually going to be the Debye sphere. And the Debye sphere for an ideal plasma is 1. So this Debye sphere is much less than 1, meaning that it is basically saying that E, or basically it's saying that E to the power over T is much less than 1. So that means that E times potential is going to be much less than T. And then therefore we could show that, okay, this is Taylor expandable. However, of course, like, you know that this is this kind of relies on a circular logic, meaning we're using a different form of Debye length to prove this temperature dependent Debye length. We won't go into the actual math for how they did it, but there are papers that show that solving actually they don't even need to Taylor expand it, but directly solving for E, they'll get the same result. So that's something that you could just trust the system, quote unquote. And then just another quote unquote fun fact: this assumption fails when R is less than or around E squared over 4 pi E T. You can simply find this by setting this thing equal to 1. All right, so now that we can Taylor expand this over here, we get this really nice answer for the plasma density, or the plasma charge density. And all we have left to do to find the potential is by just plugging this into the thing we had over here. So let's plug this in. We get this value. And then the test, of course, is going to be Q delta function. And then let's simplify this thing by setting this equal to the 1 over the new Debye length. Because traditionally, the Debye length was found through this way. I think it was 1 over T, where they ignored the Z term. And then set that equal to the test charge plus alpha, which we're going to kind of define as like just its own thing right now, which is 1 over the Debye length squared. And then you end up with this really clean equation here. So now that we have this, what do we do? Because it's kind of weird since there's a operator here, like a double gradient operator, and then just a simple scalar value. It's not like you can take this and divide, and then like take this and then just divide Q 1 over E over gradient, right? That doesn't make any sense. So in order to do that, there's actually a whole system called Green's functions designed to solve problems which look like this form. And then what you have to do is you have to have problems in the form of an operator times a function equals a second function. And then if you have problems in this form, then you can simply say that, okay, this function U is going to be the integration of the Green's function, which we don't know yet, times the function over here, integrated all over like the space that you're trying to work with. So if we look to the top, this is basically the exact same setup. The operator here is going to be gradient square minus alpha. function here is going to be u, or going to be the potential, and then function here is going to be the test charge. All right, and so from here, the next thing we want to do when looking for the Green's function is we don't actually have to try doing any like fancy math. People have done the math before us, which is why it's really nice. All we have to do is reference them and copy and paste basically. And over here, you can probably just find the Green's function necessary on Wikipedia. I'll link it in below. So when the L is going to be gradient squared plus k squared, this one's called the Helmholtz operator, then the Green's function is going to be this thing here. This is the closest kind of function that we can see that resembles the one that we have above. In this case, k squared is going to be negative alpha squared. Okay, so now that you have this here, then all you have to simply do is plug everything in. You'll notice that this is to the power of r, meaning that this is going to be in spherical coordinates. So let's turn this whole problem spherical, which also makes sense since we're working very symmetrically in spherical space since it's a test charge. Oops. And let's change the test function here now to spherical coordinates. So here is the test charge in or the delta function in spherical coordinates. It's going to be the delta of the coordinates over r squared sine theta, which is inverse of when you integrate the spherical coordinates. And now let's plug everything in to the integration. So you get this thing which looks messy at first, but it's actually a really simple answer. Why? Because first of all, the r squared sine theta cancels out with the spherical one integration on the top. So you get to cancel these two out. And then second, you can take out a lot of these constants. So q over epsilon 4 pi, take that all out. And then finally, you see over here that the only things left is r minus r prime. But since over here the delta function is at r prime, that means that r prime is at that there's no difference between r and r prime. So you can basically say that r equals r prime. And then you plug everything in here. You don't have to integrate anything. You just take everything out of the integral, and then you end up with q over 4 pi epsilon over r times e to the negative r square root of alpha. And what is square root of alpha? Well, if we go up here, it is 1 over, so alpha is 1 over Debye length squared. So that means the alpha here, that means the alpha here is going to be 1 over Debye length, or square root of alpha is going to be 1 over Debye length. And then we finally got our potential, which is really, really nice equation here. So now we want to find the dominant shielding. This was the question over here. At the top, find the dominant shielding if temperature of electron is much greater than the ion. Okay, so let's just simply get the Debye length. And then over here, we'll see that the test charge is going to be q 4 pi epsilon r. So that's just test charge. It has nothing to do with shielding. But then our shielding term is going to be e to the power of negative r over lambda d. And if it's e to the power of negative r over lambda d, then that means the lambda d term is going to be what contributes to the shielding. So we want to look at what causes this lambda d to change. So over here, we could simply figure out what lambda d is, which is directly taken from our definition here. And then we cross multiply, and we'll see that if TE is much greater than TI, which is the thermal, the temperature of the electron much greater than temperature of the ion, then Ti is basically 0 when you add it to Te, right? So the bottom term becomes only Z times Te, and the top term stays the same. And then that means you can cancel out Te, so you end up with a dependence of the Debye length on just Ti. So then that means the temperature of the ion is what dominates. All right, cool. So we got part 1 done. Which species provides a dominant shielding. And then now calculate the resulting electron density and verify that the test charge is indeed shielded by showing that the total excess charge is negative Q. Okay, so over here, the total charge is going to be integrating basically across all of space the test charge plus the plasma charge. So basically when they're asking for the total charge here, the total excess electron charge, it's basically saying, okay, the charge of the plasma, the total charge is going to be the charge of the test charge. So test plus the charge of the plasma. And then charge of the test you already know is Q. So then therefore, in order for this thing to be 0, which means that it's shielded, that means the plasma charge has to be negative Q. So that means we're figuring out, okay, we're trying to show that the plasma charge is negative Q. So to find the plasma charge, we just want to integrate this over all of space. Again, like what we did before, plug in all of our terms here, simplify, Taylor expand, since we know that we could do it, and then take out the terms, and then we're going to be left out with over here. This is as you could see from the top, this is 1 over the Debye length squared times epsilon. So let's just call it that. We're going to be left to solve this integral here. So integrate the potential over all space. In order to integrate the potential over all space, we want the potential. So good thing we solved for this before. And let's just integrate by parts and plug this in. And we will get this term here. So just a really quick note, since we're integrating over all of space and this is not radially or not angular dependent, that means you can always say that this equals 4 pi, because the sine terms becomes sine theta integration becomes 2, and then the theta integration becomes 2 pi. So overall, this will become 4 pi, and then we can take that out, and then all we have to do is integrate r. So for r, over here we have r times e to the negative r. To integrate this, you'll usually just try to use the uv minus